So, we are Hamiltonian, right. This will also become operator. So, I am going to use that this potential. So, here so it's easier to write in momentum space. Of course, you can write this as a in real space. Pi will be pi of x t, I think is pi dagger pi x t. So, we can do these operators and integrate delta function x minus x prime d cube, all that can be done in real space, but it is easier to write them in Fourier space, and in fact we work mostly in Fourier space. Okay, I think so let me just make a detour. Why Fourier space are important? And I think let's take the detour later. So let's continue right now. I will tell you about Fourier importance of Fourier space in a little bit later. So this pi squared we derived in classical fields. It was pi k pi minus k, right? You just remember few slides back. For classical it was pi of k pi of minus k, or pi k pi star k. I put mod square, no. So pi k, by the way, please remember for classical fields pi k is a complex field. Pi x was real, but pi k is complex. Okay. Here pi k and pi k dagger, now this minus k is replaced by dagger operator, adjoint operator, which is complex conjugate and transpose. So you need to do that because these are operators. So to make sense, we have some matrix, and this pi dagger k is transpose and complex conjugate. Okay. So this pi squared is replaced in Fourier space by pi dagger, which is adjoint operator, and pi k. And similarly for, so this sum is for both, sum is for this one as well as that one, and this grad phi square and p phi will give you, there is a p factor, no, remember phi k dagger phi k. Okay. So earlier it was basically phi k phi of minus k, now this phi minus k is replaced by adjoint operators. Now that is what I have written it here, and this integral is sum is integral. Okay. In 3D is that, but in higher dimension is going to be 2 pi to the power d, and this one we write as omega squared, is function of k, so we write as omega k squared. Okay. Now you can see that this is basically, this Hamiltonian is looking like a lot of oscillators, no. What was the Hamiltonian for oscillator? P squared by 2m plus x squared, right. In Fourier space, well, basically this is a oscillator potential p squared x squared. Now you can think of the first thing here is a p squared, and this is x squared. Well, you should put omega squared, right, half m omega squared k squared. So you make m equal to 1, and this is omega squared. Okay. This for single oscillator, well, no sum. Okay. This Hamiltonian for oscillator. Now for many oscillators I need to sum. So this is what I have summed. So you can think of each of these pi k's, and phi k is a momentum and position of one oscillator. One oscillator will have phi k is position and pi k is a momentum. The other one has phi k prime, and many of them. So this is a combination of many oscillators. Now it is not surprising, because what was this field for? In fact, we derived it for a string which was oscillating, no. Okay. So the string oscillations, we can think of superposition of many Fourier modes which are oscillating, right. That is the beauty of Fourier. Fourier lets you decompose into many components, and for oscillating field each component is oscillating. So that is why we have lots of oscillators giving you this this oscillation of the field. Okay. And that is one advantage of Fourier. So we are able to decompose this field equation into the Fourier basis, where they just look like sum of n oscillators. Now, as I said, it is a free field, this free. A free field is linear field. Okay. Right now, I have no nonlinear interaction. So, these oscillators are all uncoupled, they are not talking with each other, they are oscillating on their own. Okay. That is why we have nice pi squared plus x squared. Okay. When do we have nonlinearity? We can put x cube here. Okay. That is a nonlinearity. You may know some nonlinear physics, no? X cube is a nonlinear operator, and that will couple two fields in Fourier space, two oscillators. Okay. And this one we will derive it with later. So, you can couple this oscillator by nonlinearity, but right now we will assume it to be independent oscillators which are oscillating. Okay. Now, this is a classical picture, but quantum picture will also be independent oscillators, but then we will have something more. Okay. So, as I said, in classical fields we have phi star k was phi of minus k, this you can derive it. Now, this phi of minus k is replaced by adjoint operator phi k dagger. Phi k dagger is transpose complex conjugate. Okay. So, that we need to take care of, but I assure you that we do not need to construct this phi field, these operators in this course at least. Okay. We will well, some cases we will assume something, but we can just deal with particles and carry out our work. Okay. So, the Hamiltonian is this, and this is our frequency squared. Now, we can define the way we did for oscillators, creation and annihilation operators. Just pay attention to this part. Okay. I mean, this is just look at it very carefully. So, we construct a new operator, destruction operator, which is with a plus sign. Okay. So, plus is destruction operator, I made a mistake that time. So, omega k phi k plus I pi k, okay, x plus I p. Okay. So, there is I sign here, but for getting a proper normalization, omega k is put in here. So, p plus this p plus omega, well, I mean this is, well, I am not sure, this is how we construct for bosonic scalar field. Okay. This is creation operator, which I am going to explain why it is creation operator. Now, A dagger, so we can take a adjoint operator of this. So, if I take A dagger, what will I get? A dagger k. So, this is sum of two operators. So, you take adjoint of each of the operators. So, this will become 2 omega k, no problem, omega k phi k dagger, right. This is straightforward. No, I mean, here matrix is sum of two matrices and you take the adjoint. So, first one, and second one, I becomes minus I because of complex conjugate, minus phi k dagger, and this is what I got here. Okay. So, this is adjoint operator dagger. So, we have two operators A k and A k dagger. Okay, straightforward. I mean, this is a construction, I did nothing more, I just constructed given the field operators pi and phi, I created this operators. Now, it turns out we can prove it, this can be proven. So, we have commutation relations for phi and pi, right. Phi and pi do not commute, but pi commutes, phi commute. Now, I can show that A with A will commute, A dagger with A dagger will commute, but A and A dagger do not commute. It turns out A and A k dagger gives you delta function. Okay. Okay. So, this is what it is. So, there is no I here. Okay. This is the relation. Now, the delta will come because we are dealing with infinite space. Otherwise, for finite volume, you will get Kronecker delta function. I am dealing with the infinite box. So, it is a Dirac delta function. Everybody knows the difference. So, this is what we will get. Okay. Now, creation and annihilation operators. Okay, now, let us look at Now this slide is the most important one. Okay. So this is my Hamiltonian. How do I derive it? So again I am skipping the details, is kind of maybe boring. So we had pi dagger, pi k pi dagger, right. Let us go back to old pi dagger pi plus phi dagger phi. Okay. Just substitute pi in terms of a and a dagger. Okay. Like what you did for oscillator in your course, you do that, then you will get this a dagger a omega k and half. Since omega k is coming. So this derivation I am not doing the algebra, it's kind of boring to do it, especially on this board. Blackboard is better, but I will just telling you that if you just substitute pi with a plus a and phi with a minus a, you will get exactly like what you do for particle oscillators. Okay, and we get this. Now this looks very similar to what we had for linear oscillator, no? That is why I covered that one. So now here we will make a bold step. So this integral is sum of Hamiltonian for many oscillators. So as I said, each of them is, each wave number k has an oscillator, and we are just summing up over many wave numbers. Now postulate that there is a vacuum state. So vacuum state is, okay, now for every k, so is very similar to what you do for oscillators, particle, but do not think like that. You have to think that we have, for every wave number I have number of particles, for every wave number k I have particles, it could be 0, 1, 2, 3, 4 like that. So this is wave number k equal to 0, k equal to 1. Now in 3 dimension is going to be 1, 1, 1, 2, 2, 2 like that. Okay. This is schematic, so I am not saying 1, so I am just labeling them 2 like that. Now for each wave number there are particles. Now there could be 0 particle or there could be 1 particle. In fact boson, so there can be 2 particles. Here there is 1 particle, there are 3 particles here. So these are possibilities in quantum field theory. So to begin with, we just postulate there is a vacuum state which has no field, no particle in any of the wave numbers, it is an empty state. Okay, but that is a state, it is not, nothing is very important in quantum field theory. Nothing in fact is in fact it is like a ether. Okay, ether has lot of important properties. We will find that vacuum has infinite energy. Okay, so postulate vacuum state. This is like a wave function. Okay, but it is not, here particles will go away. So it is like a state, we call it state, we do not call it a wave function. So we have vacuum state where there is no particle in any of the wave numbers. Okay. Now so if there is no particle, then if I apply this ak on 0 in the state, I will get 0. Okay. So this is like a postulate. Now so we can also define a state psi. Now these properties can be proven, I am not proving it in here. So you, in general we have state psi where for every wave number k will be some number of particles. So k equal to 0 has, well I should put n0, okay, k equal to 0. So we have n1, n2, n3, nk, these are for every wave number I have number of particles, alright. So these we define, we call it state psi, right. So number of particles in each of these wave numbers can vary, is allowed, in fact it happens in real life. Electron positron pair can collide and give two photons. So this electron positron pair are gone, right. So these particle numbers can change in real life. So this is taken care by this formalism. So, we have state psi with number of particles for every levels or every wave number. Now, AK acting on psi is AK, this is a destruction operator. So, it will going to act on k wave number, kth wave number. So, this AK will not act on anything else, AK is going to look for wave number k and look at how many particles are there, there are nk particles. So, it is going to destroy one among them, okay, it just destroys it and bring it to nk minus 1, okay, and rest all particles remain unchanged. So, this is let us say wave number k. So, it just going to, so if there are nk particles, it will remove one of them, destroy it, it basically is gone in the system. So, this particle is gone. So, nk goes to nk minus 1 and prefactor square root nk will come, okay. So, these are destruction operator, but destruction operator will be different for different wave numbers, what I just told you about for wave number k, right. Similarly, we can create we have a AK dagger, it has a property, this is in the proof, in fact we can follow exactly same algebra as particle quantum mechanics for oscillator, and we will find this AK dagger acting on psi is going to look for again the wave number k, it goes there and is going to create, so it does not destroy, it creates a new particle. So, it creates a new particle, from here it has gone to there nk plus 1 and the prefactor is square root nk plus 1, okay. Now, we in fact we can use these two properties and you can substitute it here, okay. It turns out this psi is a eigenstate for H, this H is a big operator, no, it is a big Hamiltonian which has many sub Hamiltonians, and so Hamiltonian operator acting on this state psi will give you some energy, okay, because Hamiltonian gives energy and gives back the state psi. So, if I act H on psi, I will get the energy, okay. So, that is the next slide. So, it turns out this can again be proven, I am not doing it here, AK dagger AK psi gives you, in fact you can just use these two relations, right. AK acting on psi will give you nk minus 1, but now act A dagger k on this. So, AK dagger can just act on this, what will I get? So, this nk minus 1 will become nk and there will prefactor square root nk will come, right. So, nk multiplies and you get nk, okay. This given these two, it is straightforward to get that, okay. We can look at proof in any of the standard book, Lister and Bundell, which is I like this book, quantum field theory for gifted amateurs, or you can look at any book where you have all the details of the proof. So, AK dagger AK will give you nk. So, AK dagger AK, so psi is the eigenstate of AK dagger AK, just like for particles state n was a eigenstate, okay, and it gives you number of particles. So, it really works that this is basically sum of n oscillators. So, Hamiltonian will be following the same lines, this factor half is here. So, A dagger AK will give you nk on if I act on psi. So, now this guy is jumping in here, nk plus half omega k, okay. For you look at number of particles at every k, I just multiply nk plus half with omega k and I sum over all k's, okay. That is the energy of the system. Now, this is new, right, I mean classical physics cannot derive this. Classical physics we have energy was just phi square plus pi squared, right, kinetic energy plus potential energy, pi squared as kinetic energy and grad phi square was the potential energy. Now, this is purely quantum and this of course is H bar which I did not write it, and the number of particles being destroyed, created is not part of classical physics. Of course, there are interactions, so the amplitude can go down and go up, but not in terms of destruction. And so, here is discrete, number of particles can go by 1 up or 1 down, is purely quantum. Okay. So, and this half is very important factor. Okay. Now, it looks like for single oscillator we are happy, there is this quantum fluctuation and we are getting half h bar omega, right, omega. Now, there are many oscillators and each guy is giving you half, and I need to integrate this. So, what will happen to the integral? This half h over omega, but this integral is k squared dk, we know this, right. So, this integral is infinite. So, you get infinite energy in the when there is 0 particle, and there is no way out. I mean, this is coming straight from quantum mechanics formalism.